Because gas properties depend on temperature and pressure, we need to specify a particular temperature and pressure where we can make comparisons between gases. So standard temperature is 0 degrees Celsius and standard pressure is 760 millimeters of mercury. Sometimes you will see these abbreviated as STP. Combined gas law. If all variables, volume, temperature, and pressure change, we can use the combined gas law, which combines Boyle's, Charles, and the pressure-temperature relationship. Looks like this. So we have a sample of neon gas, and you notice that the volume, the temperature, and the pressure all change. We want to know what the new volume will be. Well, P1 is 1,000 torr. We can go ahead and leave that in torr. V1, 100 liters. T1, 27 degrees Celsius, that has to be, again, in Kelvin. So you add 273. On the other side, P2, we're at STP. Well, standard pressure is 760 millimeters. It's the same number in torr. So a torr is the same thing as a millimeter of mercury. We're looking for V2. And standard temperature is 273 Kelvin. Now, since the pressure and the temperature change, it's kind of hard to determine whether the volume is going to go up or down. So we'll just have to do the math with these combined gas laws to get the new volume. But it comes out to 120 liters. Gay-Lussac's law is the law of combining volumes. Gases react in simple proportions by volume. Now we're used to saying the coefficients refer to moles. Like 1 mole plus 1 mole gives you 2 moles. They can also refer to volumes. It could be 1 liter, it could be 1 milliliter, it could be any number of different volumes there. But those coefficients can refer to volumes as well. So like 1 liter of N2 plus 3 liters of H2 gives you 2 liters of NH3. So Gay-Lussac's law simply says at constant temperature and pressure, the volumes can be expressed as a ratio of small whole numbers, those whole numbers being the coefficients in the balanced chemical equation. Avogadro's law says equal volumes of different gases under identical conditions of temperature and pressure contain equal numbers of molecules. So volume is proportional to the number of molecules, which we'll call N. Try to explain this with some pictures here. I have 1 liter of N2 gas. Well, 1 liter of N2 gas, just to make it simple, contains 3 molecules of N2. If I have 1 liter of H2 gas under identical conditions of pressure and temperature, it would also contain 3 molecules of H2. So 1 liter of any gas would contain 3 molecules. Again, I'm just trying to make that simple. 3 molecules apiece. Okay, so let's go back to our balanced equation. We have 1 liter of N2. Well, 1 liter of any gas, we said, occupies 3 molecules. So there's 3 molecules of N2 in 1 liter. I have 3 liters of H2, but each liter contains 3 molecules of H2. I form 2 liters of NH3. Well, each liter contains 3 molecules of NH3. So again, it doesn't matter what the gas is. If they're identical conditions of temperature and pressure, they will contain the same number of molecules. Now here's what's important. Notice how many nitrogen I started off with. I started off with a total of 6 N atoms. I ended up with a total of 6 N atoms in the NH3. Count up how many hydrogen I started off with. Hydrogen, I started off with a total of 18 hydrogen, and I ended up with a total of 18 hydrogen. So the law of conservation of mass holds true. I did not lose or gain mass in the course of this chemical reaction. Okay, so let's do a problem kind of with Avogadro's law here. We want to produce 75 liters of NH3. And I want to know how much nitrogen would be required. These are all gases. Since they're all gases, we can use those coefficients, 1, 3, 2, to represent not a mole-to-mole ratio, but a liter-to-liter ratio. So I could say there are 2 liters of NH3, and I want to go back to N2 for every 1 liter of N2, based on these coefficients right there. So I don't have to go back to moles. I can just do a liter-to-liter ratio. And this would require 37.5 liters of N2. The volume occupied by a mole of a gas at STP is nearly constant for all gases and is referred to as the standard molar volume. The standard molar volume is taken to be 22.4 liters for every mole. Now here are some real gases: hydrogen, helium, nitrogen, oxygen, carbon dioxide. Notice how the standard molar volume is very, very close to that, what we take to be 22.4. So if I wanted to go from liters to moles, I could do so, 22.4 liters for every mole of gas. Now we get to the ideal gas equation. If you summarize all the gas laws, we have Boyle's, Charles, Avogadro's, and we can combine those into one gas law. And again, we don't like this proportionality here, so V is proportional to NT over P. We don't like that. We want to get an equal sign. In order to get an equal sign, we have to incorporate a proportionality constant, which we're going to call R. The way we're used to seeing the ideal gas law is PV equals nRT. That proportionality constant R is called the universal gas constant. It's equal to 0.0821, and it's got some weird units associated with it. But what that tells us is this: my volume has to be in liters, my pressure has to be in atmospheres, mole obviously, and temperature is in Kelvin. So the proportionality constant tells us the units for volume, temperature, pressure. So let's look at this problem here. What is the volume occupied by 13.7 grams of chlorine gas at 45 degrees Celsius, 745 millimeters? When you're using the ideal gas law, the units are important. So if I want to find volume, so we got PV equals nRT. Just kind of plug in what we know here. Pressure has to be in atmospheres. So we have 745 millimeters. We need to convert that to atmospheres. So we'll do a little conversion here. There are 760 millimeters for every 1 atmosphere. And so that's going to come out to a pressure of 0.98 atmospheres. I want to solve for volume. N is moles. Well, I'm given grams, so I'm going to take that 13.7 grams. I need the molar mass of Cl2, which is 71 grams per mole, and that will get me into moles, which is what I need. So I've got 0.193 moles. R is the universal gas constant, 0.0821. And T is temperature, but temperature has to be in Kelvin because R has units for Kelvin. So 45 degrees Celsius, add that to 273, and we get 318 Kelvin. So volume is going to be in liters when I use the ideal gas law, 5.14 liters. So again, when you're using the ideal gas law, PV equals nRT, make sure your units are in liters, atmospheres, mole, and Kelvin. We can alter the ideal gas law by substituting mass, which is a small m, and molar mass, which is a capital M. So if you're trying to solve for molar mass or you're trying to solve for density, this is the equation we're going to use. It is the ideal gas law. We're just making appropriate substitutions for N, for the number of moles. Let's look at an example. What is the molar mass of a gaseous compound? So we want to find big M. Well, we would use PV equals mRT. T over capital M. We want to solve for molar mass, the big M, so we need to rearrange this equation. When you rearrange it, it looks like this. Small m is the mass, which is in grams, so you got 1.81 grams. R is the gas constant. T is temperature. It has to be in Kelvin. We have 25 degrees Celsius, so in Kelvin that's 298. Divided by P, 737 millimeters. That has to be in atmospheres. So we're going to take 737 divided by 760 to get me into atmospheres. So 0.97 atmospheres. And then V, volume, is in liters, which is good, 1.52 liters. Now make sure these units will cancel out for you. If we're looking for molar mass, we should have grams per mole, and we do. So that means our equation is rearranged correctly, and we can solve it. So my molar mass of this compound, 30, and then the units, grams per mole, molar mass. We can also use that ideal gas law to find density. Now density is M over V, mass over volume. We've got our equation PV equals MRT over capital M, but we need to rearrange that to solve for density. So you can do some algebra. We want M over V. I'll go ahead and rearrange it for you. So we get MP over RT. Capital M is the molar mass. Well, this is oxygen gas, O2, so that's 32 grams per mole. P is the pressure. We're in atmospheres. That's good, 0.987 atmospheres. R, 0.0821 with the units. T is temperature in Kelvin, 298. Now again, what I would suggest doing, cancel out the units, make sure we have that equation rearranged correctly. We should end up with grams per liter if we have this arranged correctly. So if we want to find molar mass or density, we're going to use that alternate version of the ideal gas law. 1.29 grams per liter is the density.